Hello, boys and girls. We're here at the end of the day on Monday. I'm doing a little podcast about problem number 14 on the challenging problems. Sponsored today by GoldmanComics.com. Webmaster Ben Goldman. Ty is there behind him. Okay, I think our screen is in the window, so here we go. You're looking at the decomposition of hydrogen peroxide. Hydrogen peroxide, 2O2, goes into water and oxygen. Usually it's catalyzed by something. When we did it in the lab, it was catalyzed by dioxide. I'll change over to black to see that better. The problem, it says we want 20 milliliters of oxygen. We want to know the mass of the peroxide solution that we're going to get. So what do we need to do with that 20 milliliters? First thing in any of these problems is change our 20 milliliters into what? I think we all know that'd be moles. So we're going to need to change our 20 milliliters into moles. That's a big picture piece of the problem. And then we're going to find moles of this, and then grams of hydrogen peroxide. So how do we change 20 milliliters into moles? We know that 20 milliliters is the volume in the lab, at the lab conditions. It's not the volume at standard conditions. So we're going to need to take the 20 milliliters and convert it to standard conditions. So we have 20 milliliters of oxygen. I'm just going to change that to 0.02 liters, and you guys all know that's 0.02 liters times. If we're going to convert it to standard, we're going to need to think about this little chart: V1, V2, P1, P2, T1, T2. Volume 1, 0.02 liters. Pressure 1 would be lab conditions. Lab conditions were 95 kilopascals. Lab temperature was 298 Kelvin. 298 Kelvin. We're going to change from this 20 to what we're going to find a new volume of it at standard. So pressure 2 is going to be standard, and temperature 2 is going to be standard temperature. Incidentally, this is one of two possible ways to work this problem. The other possible way would be to use the ideal gas law. And we'll do that when we finish this way. I'll do it the other way using the ideal gas law. All right, so once again, the thing that's been difficult for people to understand in this unit, it seems like, is how do we know if standard conditions are going to be the first or the second set of conditions? The 20 milliliters that is giving us to start with, that we need to change into moles, is not at standard conditions. It tells us in the problem that it is at this pressure and this temperature. Therefore, before we can use the 22.4 to change it into moles, we're going to go from here to here. Before we can use the 22.4, we have to convert this volume to standard. So looking at the pressure ratio, the pressure is going up, so the volume is going to go down, 95 over 101.3. The temperature is going down, so the volume is going to go down, 273 over 298. And we're going to need to work out the answer to that. And then, as you're watching this, you can see that there's one other thing we may have forgotten, and that is, I may have forgotten, and that is this collected over water? It is collected over water. So the P1 here is going to be 95 minus 3.2, which is 91.8. So we're going to go back, make this a 91.8 before we work it out. So once again, it's collected over water at 298 degrees Kelvin. The pressure due to water vapor is 3.2. So of this 95, turns out that only 91.8 kilopascals were exerted by the gas, and the rest of it was exerted by water. All right, we're back here. I stopped to work it out. Ben tells me that the volume is 0.0166 liters. So at standard temperature and pressure, the volume of the gas is 0.0166. Once again, reviewing, what did we do? The 20 milliliters is not at standard conditions. We want to change the moles. To do that, we're going to use the 22.4 conversion factor. This is only valid at standard. It's only true at standard. So we must change this 20 milliliters to the volume that it would be at standard tension pressure, then use this to convert to moles. So now we've converted it. This is at STP, so 0.0166 liters times 1 mole over 22.4 liters. And that's going to give us the number of moles of oxygen that we have. Ben, did you work that out?
Yes, 7.41 times 10 to the negative 4.
Okay, so that's 7.41 times 10 to the negative 4th moles of oxygen.
Thanks, Mr. Meyer.
You're welcome. So 7.4 times 10 to the negative 4th moles of oxygen. We know that there is a 2-to-1 ratio of hydrogen peroxide to oxygen. And we also know that there are 34 grams of hydrogen peroxide per mole of hydrogen peroxide. I got this by adding up the formula weight. 16 and 16, 1 and 1 makes 34. And the final answer to that, I'll stop and work out and do it now. All right, I'm back. We worked that out. Ben, what you said this was 0.0504 grams of H2O2. And that's not the answer that's listed on the sheet. The answer on the sheet is 1.68. And the reason that that is the case is that this many grams of H2O2 is 3% of the answer. Normal everyday hydrogen peroxide that you find in your medicine cabinet is really just 3% hydrogen peroxide. It means 97% of it is water. So we know that 0.0504 is or equals 3%, 0.03 of the amount of hydrogen peroxide. So really you're going to divide both sides by 0.03 and X equals 1.68 grams of H2O2 solution. And that's your final answer. Now I'm going to move to a different color marker. I'm going to try and do this in blue. I'm going to put it over here and address a second way to do the problem. We know that we needed to find moles of oxygen. Another way, and maybe an easier way to find the moles of oxygen, is to use the ideal gas law. The ideal gas law, PV equals nRT. Seems like that's showing up in the movie. I hope it is. So PV equals nRT. We know the pressure was 91.8 kilopascals. We know the volume was 0.020 liters. We don't know N, but we know R is 8.31 liter atmospheres per mole Kelvin. And we know that the temperature was 298 Kelvin. Notice that when I set this up, when the problem was set up, notice that we had to use the pressure that was adjusted for being collected over water. Then, solving for moles, once again we will get 7.4 times 10 to the negative 4th moles of oxygen. That number is the same as that number, and the rest of the problem is the same. So you could have found moles by just simply using the ideal gas law, which is actually, I think it's easier. But you need to know both ways of solving the problem. So I think that concludes the Problem 14 podcast. Don't forget to visit GoldmanComics.com. Have a good night.